In this skill, we're going to do a quick review of complex numbers. There's no number that we can square to get a negative. So there's no number x that we can square to get -1. To be able to solve an equation like this, we introduce the imaginary number, or the imaginary unit, which is called I. And that is the number whose square is -1. So if I squared is -1, we can conclude that I is the square root of -1. There's a pattern when we raise I to various powers, and they repeat every 4 powers. So I to the first power is I to the second power, we already said, is -1. For I to the third power, if we took I squared and multiplied by another I, that would be -1 times I, which is -I. And for I to the fourth, if we took I to the third and multiplied by another I, we'd get -I times I, which would be -I squared. And we already said I squared is -1, so negative out in front of a -1 becomes a +1. Now if we multiplied that by another I, for I to the fifth power, we'd be back to I. And if we multiplied that by another I, we would get -1 again. And the pattern continues. So I to the seventh is the same as I to the third, which is -I. And I to the eighth is the same as I to the fourth, which is +1. So when you raise I to any power, you'll either get I, -1, -I, or +1. And the way to tell which one it would be is by dividing that exponent by 4. If you divide the exponent by 4 and you get a remainder of 1, then it will be I. So the I to the fifth, I to the ninth, and so on, that all of those numbers, when they're divided by 4, you get a remainder of 1. If you divide the exponent by 4 and you get a remainder of 2, like I squared or I to the sixth, you will always get -1. So I to the 10th, I to the 14th, I to the 18th, these will all be the same as I squared, which is -1. If you divide the exponent by 4 and you get a remainder of 3, then you will get the same as I to the third power, which is -I. And if you divide the exponent by 4 and you get no remainder, or a remainder of 0, then it will be +1. So looking at this example, I to the 20th, if you do 20 divided by 4, that's 5 with no remainder, so we didn't get a remainder 0, so it's going to be the same as I to the fourth, which is +1. And for I to the 23rd, same thing, we always divide by 4. 23 divided by 4, well, 4 goes into 23 5 times with a remainder of 3. And remainder 3 is going to be the same as I to the third, which is -I. In the next part, we're going to simplify our radicals that have negatives underneath them. We would think of the square root of -4 as the square root of negative 1 times the square root of 4. The square root of negative 1 is I. The square root of 4 is 2. And we always write the I at the end of the number, so we would call that 2I. 2 times the square root of negative 24 is going to be 2 times the square root of negative 1 times the square root of 24. We simplify our radical like normal, and that is going to be square root of 24 is 2 root 6. And we already have the 2 out front. The square root of negative 1 is I. And so the 2 and the 2 make 4, square root of 6, and we put the I at the end. So 4 root 6I. And the next one, same idea. Basically, the square root of the negative comes out as an I. The square root of 40 is 2 root 10. We put the I at the end, and that's over 8. The 2 and the 8 simplify, giving us root 10 over 4I. And you could write the I on the top or out front. Either of these would be fine. We always write complex numbers in the form a plus bi, where a is the real part and b is called the imaginary part. So in this example, negative 4 plus 3i, negative 4 is the real part, and 3i is imaginary, the imaginary part. And same with the next one, 5 would be the real part, negative 10i would be imaginary, and then negative 9i would be the same as 0 minus 9i, where 0 is real, and the negative 9i is the imaginary part. So the next part is doing operations with imaginary numbers, and we handle them the same way we handle other expressions. So I can add the real parts together. In this case, 3 plus negative 2 would be 1, and then I can add the imaginary parts together. Positive 5i plus 3i would make 8i. And we always leave our answer in a plus bi form. In the next one, 6 plus 4i, I'm going to distribute my negative and get minus 3 minus 6i. And then I add my real parts and my imaginary parts together. So 6 minus 3 is 3. And then positive 4i minus 6i makes minus 2i. And then in number 3, we're going to use the distributive property, or FOIL. 5 times 2 is 10. 5 times 7i would be 35i. 3i times 2 would be 6i. And then 3i times 7i is 21i squared. But we can simplify I squared because I squared is negative 1. So we end up with 10 plus, I'm going to combine 35i plus 6i to make 41i. And then 21i squared would be the same as 21 times negative 1, or minus 21. Then I combine 10 minus 21, and we end up with negative 11 plus 41i. And similar in the last one, 3 times 3 is 9. We get minus 12i plus 12i, and then 4i times negative 4i makes negative 16i squared. My positive 12i and negative 12i cancel, and so we end up with 9, and then again I squared is negative 1, So minus 16I squared becomes positive 16, and 9 plus 16 is 25. In that last example, the imaginary part ended up disappearing, and we ended up with a real number. And that is because we multiplied an imaginary number by its complex conjugate. And a complex conjugate is when you take an expression and you change the sign in the middle to be the opposite. So the complex conjugate of a plus bi is a minus bi. And when you multiply a number by its complex conjugate, the imaginary part goes away. So if we take this example, if w equals negative 5 minus 8i, we would say w bar, that's the symbol for the complex conjugate, would be negative 5 plus 8i. So I change that sign in the middle. And when I multiply these things, or find w times w bar, we get negative 5 minus 8i times negative 5 plus 8i. We distribute, we get positive 25 minus 40i plus 40i minus 64i squared. And those middle two terms with the i's cancel, and that will always happen. And then 25 minus 64i squared becomes plus 64 because I squared is negative 1. And we end up with 89, which is a real number. It lost its imaginary part. And the last thing that we will do is solve quadratic equations with complex solutions. So x squared plus 5 equals 0. When we solve by isolating x squared, we get x squared equals negative 5. And we know that there's no real number that you can square to get a negative, so it has no real solutions, but we can square root both sides of this equation to get imaginary solutions. And when we square root both sides, we still put that plus or minus, and we get x equals plus or minus the square root of negative 5, which is the square root of 5i. In the next one, we isolate x squared again. We get 2x squared equals negative 18. Divide both sides by 2, and we get x squared equals negative 9. We square root both sides, put the plus or minus on the right side, and we get x equals plus or minus the square root of negative 9. Well, the square root of positive 9 is 3, and the square root of negative 1 is I, so plus or minus 3i. And in the last one, we might try to factor this, and we find that we can't. So we go to the quadratic formula, which is the opposite of b plus or minus the square root of b squared minus 4ac over 2a. So if my a is 1, b is negative 4, and c is 8, the opposite of b is going to be positive 4 plus or minus the square root of b, which is negative 4 squared minus 4 times 1 times 8 over 2 times 1. 4 plus or minus the square root of negative 16 over 2. And in the past we would have just said no real solutions, but now we can simplify this to get the complex solutions. So the square root of negative 16 we're going to call 4i. So we get 4 plus or minus 4i over 2, which simplifies to 2 plus or minus 2i.